So, I've started. So power systems, today we are going to be looking at DC distributors first of all. But mainly, we know that a power distributor is something just used for distributing power. So just a brief overview from what we had covered last time. We talked about a power distributor and we said a power distributor can be categorized according to the voltage it is carrying, and by voltage it is carrying, we can categorize it into two categories. The first one being what we call the AC distributor, and the second one being what we call the DC distributor. So by categorizing them under those two various categories, these are the only two that we have. And now the main purpose of our study for today about the AC distributors and DC distributors is to see how we can calculate and see maybe, well, let's say when we are talking about the voltage regulation and all those other factors to do with the transmission line, want to be able to calculate maybe voltage at one point and voltage at the other point, as we shall see briefly in a few. So a brief overview of this is what I'm going to do, then strictly we shall jump into the calculations. So first of all, a distributor, we know that a power line consists of three main stages. That is, a power line consists of three main stages. That is the generation, then we go to transmission, and then we go to distribution. So Henry was saying we start with the word of prayer. I think then I will invite you to give us the word of prayer so that we can start. Since it was your suggestion, I think I can invite you to give us the opening prayer so that we can start.
No, it's okay. I'm sorry for interruption, but now you can move on since you've started. Now, for the next time, now maybe we'll start with a prayer.
No, since we have already broken off, you give us the prayer and we start.
Okay, I'm inviting our next neighbor, Sharon. If you're around, kindly lead us in a prayer. Just 1 second. Enough.
1 second.
The Maduda needful, and we push on.
Oh, sorry. Okay, let's humble ourselves and pray. Everlasting Father, we thank you for this day. We thank you for the gift of life. We thank you for the far that you have brought us. Lord, as we are going to discuss, may you help us understand. May you send your Holy Spirit to guide us in each and every step of this discussion. And may your will always be done. In Jesus' name I pray. Amen.
Amen.
Amen. Amen. Thank you, Sharon.
Amen.
So, thank you for that wonderful word of prayer. I think with that we are able to do what? To start straight away. So, I was talking about a power line, and we said the power line consists of three main stages. That is the generation, transmission, and distribution. Now, when we talk about distributors, just like the word their name is, they're used for distributing power. Now, power at a particular point, let's say if we have a transmission line, okay? If we have a transmission or distribution line, such as similar, like I'll just draw something simple to illustrate, maybe 3-wire line or something. This, now what I've drawn here is what we call an AC transmission line. So when you look at those two stages there, as you can see, by matter of fact, we don't, maybe this is a certain point A and this is a certain point B, maybe at this point A, we are picking off load to give certain household. So we are picking off a load to feed a certain household. Number one, maybe we pick one line and a neutral. Then we pick another one to give a second household. Maybe we pick one line and also a neutral. This is just a brief sketch to show what is going to happen. So by matter of fact, if this is a long transmission line, we expect that the voltage at this point not to be equal to the voltage at this point because of the drops along the length of the of the line. Okay, so that fact there is what we are mainly going to be focusing on, because we need to calculate that the voltage at this point and the voltage at this point, do they lie within the designed limits, because they have a certain thing called the voltage regulation. And this voltage regulation, maybe for Uganda, it says that the voltage at the consumer's point or contact will not always be, we should lie within plus or minus 60% of the nominal voltage. So meaning that if your system is supposed to supply 240 volts, okay, the voltage at the receiver's unit should not go below at least 6% of this value, or should not rise above at most 6% of that given value. So that is the basic thing why we have to study these distributors, and to be able to calculate and know whether the voltages are lying within the given limits. Adam Carroll, you're most welcome. So with that brief overview that I've given you, let us maybe dive into and see other things that are going to happen. Now, when we're talking about a distributor, there are things that we shall always consider. We shall always consider we shall always measure the load at a given point. The load at any point, we shall measure it in terms of current value. Okay, we shall always measure the load in terms of current, simply because when they give you, we always know that the load is measured in kilowatts. Okay, maybe a 10 kilowatt motor, a 5 kilowatt household, all that. But when it comes to power here, we shall be always referring to it. Tom monakubako okedda bambi tulikozesaako essimu ya Sharon simanyi wawe mukutte bukwasi no eri ebadde buddeko. So anyway, oba admittinze Karo alikwagala kujoininga mu adding. Just a moment, let me let these people in, and I can't see them. Let me view them. Who is that? I don't see them. I don't know if they're joining and then going out. You tell them to come in. So that I was speaking about the current and power rating, why it is equal. Simply because if they give, for example, for any system that we have, when we're talking about it in terms of kilowatts, that is the power rating. Power is equals to current times voltage. Now for any system that we have, we expect the voltage to be constant. Okay, so that means the current is the one that will change to determine our load at that specific point. So this kills the necessity for us to give our loads in terms of kilowatts or power rating, but rather we shall stick to using currents while doing these calculations. So when they give you a current of a certain thing, they are giving you simply the load of that particular thing. So for example, they will keep us telling us that maybe at a certain point we have a load drawing a current equals to maybe 40 amps. So when they give you the current rating of that load, they have simply given us the load of the load at that particular point. So briefly, those are the few things that we need to know when it comes to this. So with that, allow me to take you through the types of distributors as we had stated them, being the AC distributor and the DC distributor. Someone wants to join. Okay, so moving ahead from that, so simply the AC distributor, this one is a distributor that distributes the AC power, and then the DC distributor is one that distributes the DC power. Okay, so the DC distributor, we expected for example, an AC distributor, it can be any number of wires. It can be a 3-wire, a 2-wire, it can be even a 4-wire distributor, but it depends on what we are doing, what kind of load it is distributing to. So if it is a single phase AC distributor, we expect it to be of 2 wires. If it is a 3-phase distributor, we expect it to contain up to 3 wires or even 4 wires accordingly. But today we shall not be looking at these AC distributors, rather we shall be focusing on the DC distributors. And then for DC distributors, switching forward to what we call DC distributors. DC distributors. So for DC distributors, here we shall only be looking at the kind of power whereby we are distributing DC voltage. They carry a DC voltage. So if they carry a DC voltage, we expect a DC distributor to contain about, maybe it can be a 2-wire distributor, it can be a 1-wire, or it can be a 3-wire distributor. So when we talk about a 2-wire distributor, this 2-wire distributor only contains a positive conductor and a negative conductor, or a positive and a neutral. Okay, so that is a 2-wire distributor. It can contain positive and negative, or positive and a neutral. When it comes to 1-wire distributor, this one here we have a 1 positive conductor, and they use the earth as the neutral. So they use the earth as the neutral. So they draw 1 wire running from one end of the station to the other end of the station. Simply a 1-wire distributor looks like this. You have 1 point, you run your conductor to the other point, and at this point here, maybe it is a station. If this is my load, you pick off that wire and then you supply to the load. Then the second wire is the ground, and that will give you that wire, that single wire system. But it's usually used for very, very high voltages. So this is the plus or the positive terminal. Now when it comes to a 3-wire distributor, we expect it to have 3 wires. So 1 wire can be the positive wire, 1 wire can be the neutral, and 1 wire can be the negative wire. So that is simply the DC distributors. Those are the three basic categories of DC distributors. So moving on from that, moving on from that, we shall be looking at certain things that we expect to calculate. For example, one thing that we have talked about, if it is in a two-wire DC distributor, is that I'm trying to now to draw the basic. I'm trying now to draw the basics of what I. So I'm trying to now to draw the basics of what we shall be covering today. And now the basic thing is that when we have a two-wire DC distributor, we expect to calculate for a certain value called the voltage drop. Maybe this is one point and this is another point. And when we reach this point, at this point we are drawing off, picking off and supplying to a particular load. We are picking off and supplying to a particular load. And also at this point we are picking off and supplying to another load. So if maybe we have a voltage of maybe, let me say, 200 volts DC here, we expect that by taking off this rod, and due to the voltage drop across this section, due to the resistance of this line, we expect that there is going to be a certain voltage drop across that point. So having known that there will be a particular voltage drop across that point, that is what is going to enable us to calculate for certain parameters, as we shall see. So those are some of the basics, and I'm going to share with you my screen so that you can be able to view some of the types of distributors as we shall be talking about. So DC distributors are also divided into very multiple particular types or categories. So there are about 4 types of DC distributors that we shall be tackling in tonight's session, and all of them involve their particular calculations. So the types of DC distributors. So the types of DC distributors can be categorized according to how they are receiving power. So we have DC distributors that are fed at one end. So we can have these ones, DC distributors, number one, the ones that are fed at one end. Then we have DC distributors fed at both ends. Then we have also DC distributors fed at the center. Then finally we have ring distributors. So simply a DC distributor fed at one end is that we have the line coming in, and then we have only a certain voltage being served from one point. Remember, they are used to distribute power. So looking simply, I'm going to introduce basically looking at the DC distributor fed at one end. So type 1, the one fed at one end. Now we shall be representing the distributor by a single line diagram. So looking at it in that format, we shall say that the DC distributor fed at one end can be just a distributor like this, maybe running from point A to point B. Now when it is running from point A to point B, we are going to pick off respective loads, but it is fed at one end. So assuming it is being fed from point A, I will have it receiving particular current I. So these two arrows I'm going to be using to represent a feeder. So this here is what I call my feeder. and then this is my distributor. So a feeder is simply giving power to that distributor. So from that point to that point, we have certain points at along this axis where we are going to be picking off various loads. For example, at this point maybe I'll pick off a first load, and at this point I'll pick off the second load, and at this point I'll pick off the third load, like that and like that. Even at this point B, I can pick off my last load. So I'm going to give my loads values. Remember we said, assuming this is point, this is AB, so I can call this maybe X, Y, and Z. So if those points are X, Y, and Z, along these points here, we are going to pick off loads. And remember we said that we are going to represent our loads in terms of current. So let's give them random values. Maybe we can give this one here a certain value. Maybe my load is drawing a current of 20 amperes. Then at this point my load is drawing a current of maybe 30 amperes. This is drawing 10 amps, and this is maybe drawing also, I can say 5 ampere. Okay, so if I have a load such as that, these currents that they are drawing, you can simply see that it is easy to come up with the current flowing in the total current flowing in the entire system, because we can use Kirchhoff's law, and then we are able to calculate for the current at each particular junction. So for example, at this particular junction there is only one current flowing, and this current flowing here is equal to the current leaving, which is 5 amps. Now even at this point here, along here, we have a 10 amps flowing, and this 5 amps also flowing towards this side, but there is a particular current supplying at that point. So what do? This current is going to be equal to this and this. So this will be 10 plus 5 to give us 15 amps. Similarly, at this point we have a current that is supplying, then we have two currents leaving. So you simply keep adding from the behind, from the other opposite end coming back towards the feeder, and you're able to calculate for the total value of current flowing in that particular circuit. So when we look at this, this is 30 plus 15, it will give us a 45 amps. Then this is 20 plus 25, and it will give us a 20 plus 45, that will give us a 65 amps. Okay, so we are going to assume certain values also, and then we are able to get other values as well. For example, we can have the voltage at this point to be maybe, let's say, as we had said initially, we are taking our voltage to be around 200 volts at point A, 200 volts. So the voltage at point A, I'm taking it to be equal to 200 volts. Now, along the distributor also we have what we call the resistances of the distributor. And now these resistances here are always can be given in terms of resistance per conductor, or they can be given in terms of resistance of the entire distributor per as given length. So for example, if we have the resistance from this point to this point to be maybe R, I can call it maybe RAX. Okay, then from this point to this point I can call it RXY. Then from this point to this point I cannot call it RYZ, and similarly from this point to this point I can call it RZB. So to get the voltage at each particular point of this, maybe to get the voltage at point X, at point Y, and point Z, you simply get the voltage at the first, maybe for example if we are getting the voltage at X, the voltage at X is going to be equal to the voltage at A minus a drop appearing across this. The drop is always due to this resistance here. Okay, so after putting that into calculation, we can say that the voltage drop at the voltage at point X is going to be equals to VA minus VAX, which is this VAX is corresponding to the voltage drop along AX. So if that is corresponding to the voltage drop along AX, we can simply say, remember, voltage drop can be calculated in terms of current and resistance. So this Vx can be given by Vx is equals to V at point A minus I, the current flowing through AX, times the resistance along this point here, which is R, AX. So similarly, you can get the voltage at point X to be equals to, now our VA was 200 volts minus our IX. Now our IAX is this current here, which we had calculated by working backwards. So it will be 65 times the resistance RAX as it is given. So at that point, after putting these concepts, we can keep on calculating for the other ones, for the other remaining ones. For example, if we want to get Vy, so the voltage at point Y, if I want to get the voltage at point Y, I can say Vy is equals to, now we get the voltage at the previous point, which is Vx minus, we shall put minus the voltage drop along xy, which is Vxy. So similarly, you can calculate for that. This will be equals to Vx minus the current flowing through xy, which is 45. According to our expression, our current is 45, and then times the resistance around that point, which is Rxy. So similarly, you can keep on calculating for the entire section of the line, and you are able to get the voltages at all ends of the line along the entire length of the line. So with that, if there are no questions at that particular moment, allow me to share with you a question so that we can see one maybe example of a distributor fed at one end, and we can be able to calculate for that also and see how it is going to be done. So for those who are with me, the book I'm using, let me share with you. So the book I'm using is titled DC Distribution, DC Distribution, and I'm going straight away to example 13.1. But I'm going to do strictly one example because I want to go and look at distributor fed at both ends, so that we can be able to push on, because we have that, the one fed at both ends, and then the ring, and we have to cover both of them within the remaining 80 minutes. So this is the example that we have. I hope you can see my screen. So I hope you can see my screen. The example we have is, let me write it down a little bit, but if you can see it, you see they are saying a 2-wire DC distributor cable AB is 2 kilometers long and supplies, so they're saying the 2-wire DC distributor AB is 2 kilometers long and supplies loads of 100 amps, 150, 200 amps, 50 amps, and it is situated at meters, 500 meters, 1000 meters, etc., and so on and so forth, like that, from the feeding point A. So they're saying each conductor has a resistance of 0.1 ohm per 1000 meters. So they want us to calculate the PD at each load point if PD of 300 volts is maintained at point A. So we are going to derive the data from that expression, and we are able to maybe come up with a model of the system. So they are saying, let me share with you. So they are saying a 2-wire DC distributor cable AB, right, is 2 kilometers long. So I'm going to draw my cable AB, which is 2 kilometers long. So along here I will draw my cable, and it is from point A to point B, and I'll say this A, B. From A to B is 2 kilometers. 2 kilometers. So they're saying, and supplies loads of 100, 150, 250 amps. So they're situated along the entire length. So I'll just keep on putting the loads. This is the first load, and it is said to be 100 amps. This is the second load, and it is a load of 150 amps. This is the third load, and it is a load of 200 amps. And now the fourth load, before I put the fourth load, I want us to get something from the equation. So they are saying they are situated. So they are saying these loads are situated at distances of 500 meters, 1,000, 1,600, and 2,000 meters from the feeding point A. So point A is the feeding point. So if point A is the feeding point, I can be able to represent it as follows. So I say this point A is the feeding point. This is the feeding point. So that is our feeder at that point. And now they have told us that the loads are situated at 500, 1,000, 1,600, and 2,000 from that respective places. So from here to here, we expect the distance between these two places to be 500. So from here to here is 500 meters. Let me call this point C, point D, maybe point E. Then we expect the one from here up to here to be 1,000. So if from here to here is 1,000, that means here to here is still 500. Then the one for 1,600 is at point E. So if from here up to here is 1,600, that means we expect the distance from here up to here to be 1,600 minus already the covered one, which is 1,000. So this will leave us with a 600. Now for the last load, they said they put it at a distance of 2,000 kilometers from point A. So when they said 2,000 meters from point A. So when they said 2,000 meters from point A, 2,000 meters is similar to having 2 kilometers. So the last point is at the extreme end of the line, and it is a load of 50 amps. So it is a load of 50 amps, and it is that extreme end of the line. So if from there, if the entire length of the line is 2,000, and what we have already covered is 1,600, so we expect the remaining distance to be what? 2,000 minus 1,600, which is 400. So these are meters, 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 and meters. Let's go back and finish getting the data that is given. So they're saying each conductor has a resistance of 0.01 ohm per 1,000 meters. So the resistance of each conductor is 0.01 ohm per 1,000 meters. So after knowing that, now we are able to calculate. They want us to calculate now the last part of the data provided here. They're telling us the last part of the data. They're saying they want us to calculate the PD at each load point. If a PD of 300 volts is maintained at point A. So if this is my point A and the voltage at point A, VA, is equals to 300 volts. Therefore, they want me to calculate for the voltages at each particular point. So, given that about the above information, let us look and calculate for the voltages at each point. So we want us to calculate for the voltage at point V at C, VD, VE, and the voltage at B, because we are picking off loads at C, D, E, and B respectively. I hope we are together there. So if we're together, I'm going to push on and we continue. Okay. So pushing on from that, let us get into it and we calculate for the voltages as stated. So, first of all, before we calculate for the voltages, we shall need to know the current flowing in each particular section. And how do we find out the current flowing in each particular section? Okay, to gain the voltage, we need to know both the current and the voltage flowing in it, the voltage drop across this point, and then we need to get the current at this particular point. Sorry about that. So, proceeding from there on, we can first of all work out by getting the resistances at these particular points. So remember, to calculate the voltage drop is going to be equal to the particular current times the resistance of that particular section. But to get the resistance, we can to get the current, we can use the Kirchhoff's laws and see if we can calculate for the current. Now, to get the resistance, we shall need to calculate for the resistance individually. For example, let us begin by getting the currents, because we shall need the currents to work out this equation. So we know that there is a particular current flowing at this point, and that particular current is going to be equals to the current flowing here is going to be equals to this load current, which is 50 amps. Then from that point on, we can work backwards and get the remaining currents at each particular currents flowing in each particular section. For example, now we can get the current flowing here by simply adding these two. For example, 200 plus 50, that will give us a 250 amps. Then also the current flowing in this section is equals to this plus this. So this is 250 plus 150, that's 400. And similarly, we can get the current in this section, which is 400 plus 100 to give us 500 amps. So after knowing those currents flowing in a particular section, so we know the currents, now we need to know the resistance of each particular section in order to know the voltage drop. So we can calculate for the resistance across section SC. Now resistance across section SC is going to be equals to, you know that the resistance that I've given us is in per 1,000 meters. So that will be that resistance given, which is 0.01 per 1,000 meters. Okay, this is representing my per. So this is 0.01 per 1,000 meters. Okay, time was the distance across this section. So the distance across this section is from A to B is 500 meters. Now remember that this resistance that they gave us was for a single conductor, but we are all aware that a DC distributor, the ones that we shall be looking at always considering a two-wire DC distributor. So even if they haven't mentioned it, we shall need to multiply the value that we have got by 2. So this will be times 2 and finally the answer we shall get, I don't know, let me get my calculator, is going to be the resistance across that particular section. For example, this is 2 times 500. For 2 times 500 is 1000, so times 0.01, that will give us a 0.01 ohms across that particular section. Thank you. So that will be the resistance across that section. Then we can calculate for the resistance across section CD. So similarly, resistance across section CD is going to be, because we said it's a two-wire distributor, times the resistance per 1000 meters times the length across that point, which is 500, and this is going to give us the same answer since they are mathematically identical. That will give us 0.01 ohms also. Then similarly, we can calculate for the resistance across section DE, and the resistance across section D is going to be the 2 for the number of conductors times the resistance, the resistance per, so times the resistance per 1000 meters, then times the distance across that section. The distance given there is 600 meters, so we shall use times 600 meters, which is going to give us, I think when I calculate for that, it will give us a 0.0. Let me press it here, right here. So it's giving me a 0.012 ohms. So thereon we can calculate also for the resistance of the remaining section, whose distance is 400 meters. So from there on we can calculate for the resistance across section. It is what? EB being equals to 2 times 0.01 over 1000 times 400 meters. These are all in meters, so the meters, the units are the same. So when you get this,
Excuse me.
yes,
What do we divide by 1000?
because the resistance they've given us there is per 1000 meters.
So we are changing them to kilometers.
No, not to kilometers. The resistance given is per 1000 meters. So they're saying each 1000 meters of the conductor is containing a resistance of 0.01 ohms. But what about the resistance of 500 meters? So it will be the resistance of 1000 divided by 1000 times 500. It's simply like a unit conversion. Maybe to elaborate it, let me write it for you down. So here they have given us that. So what they have simply done there is they have told us the resistance for 1000 meters is, sorry, I hope you can see my screen. The resistance for 1000 meters is 0.01 ohms. Okay, now what about this section we want? This section is 400 meters, so the resistance for 400 meters is going to be 400 meters over where we are moving from, over 1000, okay, times where we're going, which is 0.01. So simply this, but it was for a single wire. So because it was for a single wire, we shall multiply times 2. So you can see that this is identical to this. That's why I preferred to use this kind of nomenclature to ease the work. So from that, I hope we are together, Carol.
Yes.
Yes. So from that, when we tap that into the calculator, we are able to get a resistance equal to 0.0, yes, 0.008 ohms. So those are our resistances per section, or per section. So moving on from that, we have calculated for the currents. We can get the voltage drops across the entire section, and then we calculate for the what? We calculate for the voltages at each particular point. Okay. So from that, what we have been provided there, assuming we want to calculate for the voltage at point C, the voltage at point C is going to be equal to the voltage at point A minus the drop along this point. So from that, briefly, so from that, calculating using that, we shall say that the voltage at point C, which is VC, is going to be equal to voltage at point A minus voltage drop along AC. So this is going to be equal to the voltage at point A, and they told us the voltage at point A is maintained at 300 volts. So we shall use 300 volts minus the voltage drop along SC. Now the voltage drop along SC is going to be equal to the current flowing through that section, which is ISC, times the resistance across that section, which is RSC. So using that, we can calculate for that voltage, and we shall say this is going to be equal to 300 minus the current flowing through that section is this current which we have calculated, which is 500 amps. So minus 500 times the resistance across that section. Now the resistance across that section is what we have calculated here, the first value of resistance, which is 0.01. So pressing that into the calculator, we are able to get 300 minus 500 times 0.01. So that is giving me a total voltage of 295. So the voltage V at point C is going to be equal to 295 volts. So similarly, we can calculate for the voltage drops along the entire section in that same way. So proceeding on, let us calculate for the voltage at point. Let's calculate for the voltage at point D. So similarly, the voltage at point D is going to be equal to, now we shall always get the previous voltage, which is VC. So we shall get VC minus the voltage drop along this section, which is going to be equal to VCD. Now, knowing that, we shall get that the voltage at point D is going to be VC minus VCD, which is going to be equal to the current in that section, which is ICD, times RCD. So putting that into consideration, we can calculate, because we have these particular values. So this VC is the value that we calculated earlier on. So our VC is this previous value of voltage, which we calculated, which equals to 295, minus ICD. Our ICD is going to be this 400 amps, which is 400, times the resistance across CD. Now the resistance across CD is what we calculated earlier on, and we got this particular value of 0.01. 1. So putting that also into the calculator, we can have 295 minus 400 into 0.01. So that is giving me a voltage of 291 volts. So my voltage at point D is going to be equals to 291 volts. Now the rest is simply a repetition of what we have done before. We are going to keep on doing and doing and doing for all the remaining sections. So for example, also we calculated for V at D, let us calculate at VE and VB respectively. So to get voltage at point E is going to be equals to the previous voltage, which was voltage at point D, minus the drop along this section. So it will be equals to VD minus voltage drop along the section, which is VDE. So this will be equals to still VD minus IDE, the current flowing through that section, times the resistance of that section, which is RDE. So VD is going to be equals to our previous value of voltage that we got, which is 291 volts, minus the respective value of current flowing in that section, which is, for this particular section, it is 250 amps. So we shall use that 250 times the resistance across that section. So the resistance we had calculated earlier on was RDE to be equals to 0.012. RDE is equals to 0.012. So we shall calculate using that value and feed it back in 0.012, and when we feed that into the calculator, we get 291 minus 250 times 0.012, which is giving us 288 volts. So similarly, you can calculate for the voltage at the last point, which is voltage at point B. So similarly, voltage at point B, VB, is going to be equals to the previous voltage, which is VE, minus voltage drawn along EB. So that is going to give us our VE, which is what we calculated earlier on, 288, minus the current flowing through this section, which is 50 amps. So we shall use that and say minus 50 amps times the resistance across that section. The resistance across that section, and the resistance we got, the last value of resistance was 0.008. So we feed that also into the calculator. So we get 288 minus 50 into 0.008, and the value we get there is the answer, which is giving us 287.6 volts. So that is the voltage at point B. So like that, that is simply how we calculate for the voltages at each particular section along that given line. So clearly you've seen that our voltage at point B is always the least, is having the least voltage. So when they ask for the minimum voltage, the minimum voltage is this point here, where we having the least value of voltage. We got VBE to be equals to 287.6, which is a very small value compared to all other values of voltage along that line. And similarly, when they ask you about the maximum voltage drop, now when they ask for you for the maximum voltage drop, is simply the voltage drop from point A to the point of minimum potential. It is always from the point of maximum potential, which is usually the supply, to the point of minimum potential, which is usually this what we have calculated here. So VAB is maximum voltage drop. So, are there any questions regarding to that question that we have just tackled? If not, I'll be maybe giving you a few hints, then I switch directly to distributors fed at both ends. A moment of silence as I wait for your questions. If there are no questions, just tell me to proceed. Any questions?
Proceed.
People understanding. No questions. Okay. So that is briefly it. So from that now allow me go to what we call distributors fed from both ends. Oh, sorry. Before we go to that, I wanted to give you a few hints. Now the few hints are simple. In this case here, when I look at this question here, they gave me what they called resistance. This value here, they gave me resistance of each conductor. Okay, they mentioned that the resistance of each conductor is this value. So there's going to be certain times when they can give you this and they don't give it to you in terms of resistance. They give it to you in other kinds of values. They can give it to you in terms of resistivity, and when they give you resistivity, they will give you also the cross-sectional area. Okay, so they can give you that maybe I'm going to use a scenario, explain a scenario kind of situation to explain this. So for example, if they give you that it's still a two-wire DC distributor uses copper, okay, of resistivity they give you resistivity, which is always given as that being equal to a certain value, maybe 2.75 over exponent what, I don't know the exponential value, but they will always state it, but I'm just using that 2.75 exponent negative 3, maybe something like that, but they've given you the value of resistivity. So when they give you resistivity is a standard value. It does not cater for both of the wires. It caters for only because it is the material. So it is a two-wire DC distributor having a resistivity of that, and then they give you, maybe they can give you the diameter of the conductor used. Diameter is maybe, let me say diameter, how can I give diameter in centimeters? Maybe I give it to be, let me say 2 centimeters. Yes, is maybe 2 centimeters diameter. Now this is centimeters, and now they give you all the other specifications of the line, the distances, the loads being tapped off at particular points along the conductor, and generally everything is looking the same. This is point A, this is point B, this is C, D, E, maybe F, and are giving us particular loads being tapped off at those particular sections. Maybe we can call this one to be I1 or I2. Okay, maybe let's give these values currents, current. Then we shall calculate previously as we had done, so we shall calculate for just a moment. I still have about 40 minutes. Hey, do you have type C charger? Of course. So I was saying that they give you the values of the respective. So we shall do the same thing. We shall calculate for the currents in each section, and each section like that. maybe we shall call this one, maybe let me call it I1, I2, I3, I4, I5. Now the only thing that is going to change is when it comes for you to calculate the values of resistances across the particular section. So first of all, what they have given you here is diameter. First of all, when they give you diameter, you need to calculate for the area, being equals to pi d squared over 4. But since the distances we have been given here are in terms of what? Meters, it is always advisable for you to convert your diameter into meters. So my diameter, for example, my diameter is equals to 2 centimeters, which can be expressed as 2 over 100 in terms of meters, to give me 0.002 meters. Is it? Yes, 0.02, like that. So I'll come and use that to calculate for my area. So my area is going to be simply equal to pi times 0.04 but 0.02 squared divided by 4. So after calculating for that area A, we shall use the formula for resistivity or resistance to calculate for the resistance. We know that resistance is directly proportional to what? Is it directly proportional to? So resistance is going to be equal to resistivity times length over the area. Okay. Now, what I told you that here it is a single, it is a two-wire DC distributor, but resistivity only caters for one wire. So when you're feeding in for this calculation, you'll have to multiply for this times 2 to cater for the 2 wires of the what? Of the distributor. Are we together there? So we shall always mean to multiply the value. If whenever we're given resistivity, we shall always need to multiply by 2 to cater for the both resistances of the 2 wires. Remember, a DC distributor has 2 wires. Resistivity they have given us is of copper, and it only caters for only a single wire, so we multiply it by 2. So after doing that, you can calculate for your resistances along this point, this point, this point, and then you proceed like we had previously done. So I'm going to add the members to try out numbers having resistivity, and then you see how you can arrive to the answer. So when you come to this section, the area has been calculated, which is this. The resistivity is given. Now the length you use is the length of each particular section. The length of each particular section. So I would like to invite any questions before we move on to distributors fed from both ends.
Carol, please ask something. Stop being quiet.
So, as we wait for a question, I can see here. Sorry, there is a question here. Yes, ask a question.
When we go back to maximum, maximum voltage drop, does it mean that you have to add all the dots from A to B, then the total is maximum voltage drop?
Yes, it means you have to calculate for the total voltage drops along the particular line from point A to point B. So for example, if we want to get the maximum voltage drop, is going to be equal to the total voltage drops at this point, this point, this point, this point, up to the point of minimum potential. If point B is our point of minimum potential and point A is our point of maximum potential. So someone wants to join. Admit, okay. So maybe Sharon screenshot. So anyway, what I was saying is that if I now this thing of point of maximum voltage drop will find significance when we are doing with the ring distributors, simply because for these ones here, the maximum voltage drop will just simply be voltage drop from point A to point B, which is simply adding every one along this, every one of the drops along this line. But when it comes to ring distributors, we shall find the significance, or even distributors fed at both ends, we shall find the significance of that value called maximum voltage drop. So, now I'm going to move to this distributors fed from both ends, and maybe we can see how to calculate for that drop in case we are asked to. So with that, allow me to move on. So we are going to move on to distributors fed from both ends. So let's look at this distributors fed from both ends. So what I was trying to share with you last time was just a sample question before there was a change in what? This was the sample question whereby they have given you resistivity from the previous example, okay? So they have given you resistivity and they have given you even the area of the conductor. So here they have eased your work. You can simply work it out as we had earlier on said. So that is briefly it. There are some of the problems that we have. Then let's look at let me go directly to distributors fed at both ends. So what we have done, before even I go any further, there is a concept that I hadn't yet explained a little bit. Allow me to go back a little and show you what that concept is. It's not briefly a calculation, but it is just simple. So what I had here previously, now these loads that I'm tapping off at particular points along the conductor, these loads are what we refer to as concentrated. These loads are what we call concentrated loads. Simply they are appearing at one point along the entire length of the transmission line. For example, this appears here, 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 and here as individual loads. So they are concentrated loads. But then also we have what we call uniformly distributed loads or distributed loads. They are distributed and told along the entire length of the distributor. So they are not concentrated along one point, but they are distributed along the entire length of the distributor. So what we shall be calculating here mostly, it will be dealing with what we call concentrated loads. So when they mention something to do with concentrated loads, you know that they are just at particular points along the section of the conductor. Okay, so let's move on to DC distributors fed from both ends. So what I was trying to explain is that we can have a distributor that is being fed at more than one end. For example, a typical example that I can give is this that I'm going to draw here. So if I draw my distributor, maybe distributor A up to B. So it is peaking power so it is peaking power at a particular point, maybe point A, and running up to another end of the line, which is end B. Now yes, it is running up to another end of the line, maybe end B. So it can be supplied with power from each of the opposite ends. So it can be having a feeder at point A, and it can also have a feeder at another point B. Okay, so these are my feeders like that. Then we can always have loads being tapped off from along the entire length of the line. So for example, I can have those loads to be, let me call it load, let me say I1, I2, and I3. So now when it comes to such a particular kind of a scenario where we have a certain voltage at point A, maybe V at A, and then there is a voltage at B which is voltage at point B. Now the current that is going to flow within this particular section, the current that is going to be particular section will be as a result of currents moving from both directions. So for example, I'll assume that this side will bring current and this side will bring current, and maybe also this, what passes here, some of it will go here and some will go here. Now when they reach here, both currents are meeting and supplying one load. So when they meet and supply one load, there is what we call a point of minimum potential, and I'm going to explain that. But first of all, we have to know that the currents will be coming from both directions. Okay, so after knowing that they will come at both directions, we can have a point, maybe this is A, B, let me call this X, Y, and Z. So let me call this point X, Y, and Z. So after knowing this is point X, Y, and Z, we have a point called the point of minimum potential. Just like what we had previously in the previous example. Even here there is a point of minimum potential, but this time round the previous point of minimum potential is not this end and not this end, but rather that point whereby current begins to change direction. So for example, here current is being moving into from this direction and also from this point of direction. So point Y becomes my point of minimum, minimum potential. So you're going to find that if maybe this is my supply voltage, let me say my VB, maybe let me give it maybe 240 volts, and then I give my VA to be maybe 230 volts. You're going to find that the voltages will drop along this point, but you'll find that the voltage at Y will be far small. Maybe this is going to be maybe 2, let me call this one maybe 235, maybe this is going to be maybe, let me say 230, 229. Okay, you're going to find that the voltage at Y will be always smaller than any of these two. Let me give it 220. So you're going to find that voltage at Y is going to be always smaller than any of the other two that you've had in your line. And that is one of the points that we need to have in mind. So whereby the voltage, where the currents begins to change direction, that is our point of minimum potential. Now let's look at another thing that we shall be considering in this section, maybe to calculate for the particular currents. Now since current is moving from this direction and also this direction, it becomes so hard for us to calculate for currents at each particular currents flowing at each particular junction. Okay, so what we are going to do is, whenever we are provided with such a line, the method we are going to be using is going to be simple. We shall have the line like that. It shall always have its feeders, maybe at point A, and also a feeder at point B, like that. And then we shall tap off the respective loads as previously done, like that. So here, along that section of the line, along this section, I'll have my current. Okay, maybe let me call this one I1, this I2, and this is I3. I've decided to call my points X, Y, and Z. This is X. So here we don't know the point of minimum potential. We don't know the directions current are flowing from and where they are heading to. So what I would advise you to do is simply consider from one direction, any of the directions you use. You can choose from A, working from A towards B, or you can use to work from B towards A. But since most of us write coming from this side to the other side, it is easy to work from point A towards B. So I will assume, okay, so at that point, I will want to assume that my major current is coming from point A, and it is going to be moving in this particular direction, like that. So if I call the current flowing here to be any unknown value of current, maybe I can call it the source current IS, okay? The source current IS being an unknown value. So the current that is going to flow between this section and this section by Kirchhoff's law, it is going to be equal to this supply current minus the current being tapped off, not so? So this will be IS minus I1. Then when we reach this value here of current, the current flowing here is going to be equal to this current minus the current being tapped off. Sum of currents entering equals to sum of currents leaving. So IS is equals to this. Okay, IS is going to be equals to this unknown plus this. So that means this unknown is going to be simply IS minus that. Same way we shall apply here the same principle. So this will be this current flowing here. Let me pull it down here, and I'll say this current flowing there is going to be IS minus I1. Okay, but this whole thing is going to be subtracted minus I2 because it's what we are tapping off, so minus I2. Similarly, if you want to calculate for this current here, it is going to be equal to the current flowing here minus the current that is being tapped off. So this will be IS minus I1 minus I2 minus I3. So that is how we find the currents flowing in each particular section. Okay. Then after finding the values of current flowing in each particular section, we expect that we should be able to calculate for the voltage drops along each point, and then maybe to calculate for the values of voltages along at each particular tap-off point. So with that, allow me to choose one example that we can work with and see how this is done. So I'm looking for an example, worked example maybe. So here we have an example. Let me share with you. So I don't know, this figure is for which example? 2 ends, yes, this. So here we have example Let's look at example number 13.10. So there we have a 2-wire. Who can read for us? Mr. Davis, you can read for us so that I know we are together.
Okay, let me read. A 2-wire DC street mains AB 600 meters long is fed from both ends of 220 volts. Loads of 20 amp, 40 amp, 50 amp, and 30 amp are tapped at distances of 100 meters, 250 meters, 400 meters, and 500 meters from the end A, respectively. If the area of cross-section of distributor conductor is 1 centimeter squared, find the minimum consumer voltage. Find the minimum consumer voltage. Take rho as 1.7, but take resistivity equal to 1.7 times 10 power negative 6 ohm centimeter.
Okay, thank you for that. So let us dive in. The question is given already. Let us dive in and see how we can calculate for this particular. So let's dive into the equation and see how we can come up with the solution. The first thing is to come up with a model of the line. So they're saying a 2-wire DC distributor street mains AB is 600 meters long. So we are going to draw our line, being a line maybe AB as they have stated. So A to B, and they have told us AB is 600 meters long. So AB equals to 600 meters. Then they are telling us that it is fed at both ends with 220 volts. So if this is my feeder and this is my feeder, we expect that the voltage at point A and is equal to the voltage at point B, which is 220 volts. So that means the voltage at point A is 220 volts and voltage at point B is also 220 volts according to that equation. So according to that question. So it's saying loads of 20, 40 and 50 amps, 20, 40, 50 and 30 amps are tapped along the distributor at those respective distances, as you can see. I'm going to tap off my loads. Say my load 1, 20, and load 2, load 3, and load 4. So I'll tap off my loads. My load at point A is going to be 20 amps. Load at point B is 40 amps. Load at point C they have given us to be 50 amps. And then finally the load at point D is 30 amps. So they have told us their respective distances are the following values. So the distance from point A, let me assume these points are going to be, let me call these points, this is A, B, so I can give this C, D, E, and F. So the distance between AC is going to be 100 meters. Yes. So from A to C, from there to there is 100 meters. Then C to D, the distances are measured from point A. So from point A to point D is 250. That means from point C to D is going to be 150. Simply subtract 250 minus what you've got there. Then D to E, so from A to E is 400. That means from D to E is 400 minus 250, which is 150. Then find D to E. Similarly, they have given us from here up to here to be 500. So we are going to take 500 minus these values here, which is 400. So 500 minus 400, that is going to give us 100 meters. And finally, F to B. So when you go to F to B, they have told you the distance from F, from A to F is going to be, from A to B is 600 meters. So you just get 600 meters minus 500 meters to give us this remaining distance, which is also 100 meters. So there we have got the respective distances between the loads along the line. Now when you proceed down further, they are telling us if the cross-section area, they're saying if the cross-sectional area, just a moment. So they're telling us that if the cross-sectional area, so they're telling us that if the cross-section area of the conductor is 1 centimeter squared. So the cross-sectional area they're giving us, just to share with you. So they're telling us that if the cross-sectional area is 1 square centimeter, so the cross-sectional area they're giving you is the cross-sectional area of the conductor. So let me take you back again so that we can proceed. So that is the cross-sectional area. I can say the X area is equals to 1 square centimeter. Okay. And now they want us to find the minimum consumer voltage. So they want us to find V minimum. Okay. They want us to find the minimum consumer voltage, which is the voltage, the minimum voltage that can appear across the entire length of the line. And then they are saying take resistivity rho to be equals to, so they're telling me to take resistivity rho to be equals to 1.7 exponent negative 6 ohm centimeters. Now this value of resistivity is in ohm centimeters. So it is in ohm centimeters. And remember, what we want to work with is in meters. So now there we shall have to do some unit conversion. But before we reach that point, let us first proceed with this and maybe come up with the equations. So step number 1 we had said is to come up with the particular currents flowing in each branch. Okay. So we are going to choose to work from any one direction that we want, and then we shall assume a current, and then we shall find it later on. So for example, we shall assume that the current flowing through maybe SC, let's call this maybe IX, an unknown current IX. So if that is a certain current IX that we don't know, that means the current flowing here is going to be this IX minus this current here. So that is going to give me IX minus 20. Okay, so proceeding further, for those who are asking if the session is being recorded, yes it is. It is being recorded and it will be shared. So let's go further to this remaining part of the section. So From there on, we shall also calculate for the voltage at this remaining point here, DE, between DE. So the current flowing through point DE is going to be equals to this current minus 40. So it will be Ix minus 20 minus 40. That will give me minus 20 minus 40. That gives a negative 60. So the total current flowing here is going to be Ix minus 60. Similarly here, shall do the same. This will be this value here minus 50. So that will give us minus 60 minus 50, that is Ix minus 110. Then similarly, the current flowing here, we assume it is going that direction. It will be this minus this. So this minus this will give us Ix minus 140. And those are our respective currents across each section. Now, here comes another situation whereby we have to reason it out and see how we can do it. For example, when we reach this particular point, we shall need to calculate for the voltage drop. We shall get the total voltage drop along this section, which is going to be equal to simply adding the resistances. But we go to that, before we go to that, we need to calculate for the individual resistances of each section. So let me say we calculate for resistance of each section. So to calculate for the resistance of each section, we shall get now from our formula of resistance is equals to density times not density, that is resistivity times length over area. But we said since resistivity only caters for a single conductor and we are working with two conductors, shall always multiply it by a 2. Now let us get this value of resistivities. So for example, this was given in ohm centimeters, this was given in square centimeters. We shall need to calculate for these values in terms of meters in order to be able to do what? To find out the particular thing, so that we cannot confuse ourselves. We can change them to meters, or we shall change the meters to centimeters, whichever value you choose. So this value here, so how do we change the length into how do we change resistivity into centimeters, into meters? So this is resistance ohm centimeters. So this value is in centimeters. To change to ohm centimeters, so to change it to meters, we shall multiply it by 100. Now when it comes to area, for area we shall need to divide it by, okay, for area we shall need to multiply it by this 1 centimeter squared is simply meaning when we have area equals to centimeters squared, it is simply meaning centimeter times centimeter, not so. So to change this thing into meters, we shall need to multiply it by 100. We divide them by 100. We divide them by 100. So similarly, this one we shall need to divide by 100 times 100. Okay. So we shall divide them by 100 times 100, which is meaning it is the same as 1 out of 10 to power 100 times 100, that's 1, 2, 3, 4. So that gives us what we get, 10 power negative 4. Okay. Anyway, I hope we are together there. Now we can calculate for this value alone, and then we see how we can utilize it. Mm. Or simply you can calculate it in terms of also centimeters. So there are two different ways, as he had explained last time. You can choose to change the centimeters to meters, or you can choose to change the meters to centimeters. So our resistance I hope you can see my screen. Just a moment. So our resistance, maybe you can calculate for the resistance per meter, okay? Now, if I don't want you to suffer so much, it is easier to leave them in centimeters, then you convert this unit into meters. So resistances, now I'll show you the way I would prefer to do it. So resistances per section. Let us go directly and calculate for the resistances per section. So if we want to calculate for the resistance between section A and C, maybe, for example. So the resistance between A and C is going to be equals to 2 times resistivity times length over area. Not so? Like that. So that is going to give me a 2 times now my resistivity. I can leave these values since they are both in centimeters. I just change my value for the distance across these 2 meters from meters to centimeters. So it will be value of 2 times the resistivity, which is 1.7 exponent negative 6 divided by the area, which is 1 square centimeter, times my distance is 100 meters, but 100 meter, each meter contains 100 centimeters, so it will be times 100 times 100. Okay, so this one you will give me, after calculating for it, this value will give me a 2 times 1.7 exponent negative 6 times 100 times 100 so it is giving me a total resistance of 0.034 ohms. So that is my resistance across section AC. RAC equals to 0.03 ohms. We proceed and calculate for the resistance across the remaining sections like that. We can calculate it simply using that. Sorry, you're saying I was assuming, what if the current is decided to flow from point B to A? What happens? When you want to ask a question, I beg that you unmute and speak, because I may take so long to read the messages, because when I'm writing this side, I may not be able to read the messages. But if you to choose the current to flow from end B to point A, that means you'll consider the current from this direction, and therefore you'll just keep subtracting. Maybe this is IY. The next current here will be simply IY minus 30. Then IY minus 30 minus 50, which is IY minus 80. Then you keep on doing the same thing, but towards the opposite direction. You have to just follow the same rules. Just have to keep on following the same rules. I hope that is answered. So let us proceed and calculate for the resistances across the remaining sections. For example, resistance across CD. So the resistance across CD is going to be equals to 2 times the value of resistivity, which is 1.7 exponent negative 6, times the length. The length between this point and this point is 150. That is in meters, but you change it to centimeters to give us 150 times 100. Okay, so from that we can say 2 times 1.7 mu times 150 times 100. So that is giving me a 0.051 ohms as resistance. So the resistance across that section is 0.051 ohms. Then we can also find the resistance at the other section, between section RD E, and the resistance between that section is going to be similarly the same to, it will be that value of 2 times the value of resistivity 1.7 exponent negative 6 times the value of the distance between D and E, which is also 150 times 100. So I assume that since they are the same, I'm so sure that the answer that I will get is the same here. So it will give me 0.051 ohms. And then also we get for the value of resistance between EF, if we have F, yes, from EF the distance is 100, so it will be 2 times 1.7 exponent negative 6 times 100 times 100, which is what we had calculated earlier on, and it will also give us a value equal to 0.034 ohms. Then similarly we can calculate for R between F to B, and that is going to give us also 2 times 1.7 exponent negative 6 times the distance between these two sections, which is equals to, now the distance there is also 100, so it will be times 100 times 100, and this is going to give us a value of also the same value, which is 0.034 ohms. So any questions at that point? If there are no questions, we are going to go to the final section of this calculation, and then we shall be able to get our final voltage or the minimum voltage as requested. So if there are no questions at that particular point, let us proceed and try to calculate for the unknown current. Remember, for us to be able to calculate for the voltages between voltage at C, voltage at D, voltage at E, we need to know the current flowing through each particular section. For example, this unknown current needs to be known, this current flowing here needs to be known, this needs to be known, these are like that, and so on and so forth. Then we shall be able to calculate the drops, because the drop uses the current times the resistance. The resistances, we have calculated them right here using that particular method. So that is where we are going. Let us look at how we can calculate for the values of resistance at that particular point. So let us proceed and calculate for the values of the current flowing in the sections. Now, referring to this diagram as earlier we had drawn, we are going to be able to calculate for the currents flowing in each particular section. How do we do that? To do this, we shall get the total, like maybe the entire drop across the section. Remember, the entire drop section, voltage drop along A, B, is going to be equals to, hold on, just a moment, before I go to that, yes, so the voltage drop along that particular entire line as I was saying, is going to be equals to the sum of the individual drops along this time. Okay, so it is going to be equals to Ix times the resistance across that section RAC plus Ix minus 20 times the resistance across this section, which is RCD, plus the current flow in there, which is Ix minus 60 times the resistance across that, which is RDE, plus the current flowing there. You keep on doing the same thing, which is Ix minus 110 times the resistance across that, which is REF, plus finally the current flowing there, Ix minus 140 times the resistance across that point, which is RFB. But remember also that the voltage drop across A and B can also be got by getting voltage at point A minus voltage at point B. Okay, is that true? Yes, sir. Online, are we together at that point?
Yes, we are together.
Yes. Thank you. So moving on at that point, we shall get to, so we shall say that VA minus VB is equal to the sum of the total drops along this point. Just that, like what we normally did in I think network theory. So from there, let's move on and calculate for that. So VA, my VA minus VB is going to be equals to this value of Ix times my value of resistance, which was RSC value, we got 0.034. Okay, now plus this value here, RCD, our RCD we got was 0.051. so here hey, someone is calling. So oh, network angebuzi over data. Yes, it's.
Yeah, it's 0 now.
Let me get who's
What should we
eyo kweli.
It's there. It's already done.
So kompenga ke eyo connecting ekaku bagiyita bakya Infinix. Come which one is that? Jesus. I did the one. Go on. Now I'm not seeing her phone.
It's not come on playing.
Yeah, I've seen it. Let me be connecting a little bit. It's taking years to connect.
This you then let's put on this one that is already
Okay.
okay.
But I don't yeah, why? Yes. Any which is available.
Cesar, why are you interrupting our network?
Sorry, we are coming. I I think a connecting is a common.
Connecting.
Yes, it has connected. I don't know. So hello, are we back?
Let me see.
Can you hear me?
You got me
I can't see anything.
rejoin. Are you seeing us?
No.
Can connect to your phone? Because I don't have data.
Sorry.
It is working.
I've connected to someone's Wi-Fi, but I'm not seeing the meeting. Google Meet, where are you? Ate wendiva mbeera sisobola kugiddamu.
It was that I forgot to tell you. I checked here. It was 100.
Let me join this again. I'll join again. Tidio wandiko saya. Hello. Options. Let me pin for everyone. Yeah. Sorry. Who are Soko tole kugoni volume. Hey.
It's on. And I'm not connected.
So let me see. Who is this? So hello. I don't know. Am I having feedback? Microphone yanyo eriko. I have two of them. Let me remove one of these.
First, we are ready to see here.
You can see me.
A. Let's screen.
So sorry about that. I hope you can hear me clearly. Now I was explaining something and we went off a little bit, but let's get through this and then we can see what to do. So what I was saying is that here we have our voltages at this particular point, and we were calculating the voltage drop along the entire length of the line. So for example, VA minus VB is going to be equals to the sum of the drops along the entire length of the line. So we are just simply substituting what we did here. For example, this was the value for RCD and this is the IX. Now similarly, we are going to go and pick the value for RCD, which we calculated to be 0.051. So it will be 0.051 times the value of the current flowing there, which is IX minus 20. So this will be plus RDE. Our RDE value is still 0.051 times IX minus 60. So this will be plus also our IX minus 110, but all multiplied by the value of REF, which we calculated to be 0.034. Then similarly, we can do the same for the last one, which is going to be our RFB value, which is also 0.034 times the value of resistance across that section, which is IX minus 140. So from that, what is left is to simply compute the values. The value for VA and VB are the same. So this will give me a value of VA. The value for VA they gave us was 220, and VB was also going to be 220. So this is going to mean we shall have a 220 and as a 220 here, and this will give us a 0. So I'll have that my 0 is going to be equal to, now what I do here, I will first of all add my values of Ix. So the first one is Ix plus the second value here is 0.5 times Ix, 0.05 times Ix plus 0.05 times that plus 0.03 times that, like that, and so on and so forth. So it is what I'm going to do entirely throughout that computation. So it is, the first one is Ix times 0.034, so it will be 0.034 plus 0.051 Ix plus 0.051 Ix also plus 0.034 Ix plus also 0.034 Ix. So this is giving me a total value of 0.204. So this is going to be 0.204 Ix. Then here I'm having all these values here I'm having are going to be negative. A minus this after multiplying, a minus this, a minus this, and a minus this after opening the brackets correctly. So when we do that also, let us do that and see the value we come up with. So when we do that, summing them up, that is going to give me a 0.04. That's going to give me a negative 0.051 times 20 after opening this bracket, then plus a negative 0.051 times 60. So times 60, then plus 0.034 times 110, then plus 0.034 times 140. So that is giving me a total of negative 12.58. So this is going to give minus 12.58. So from that we can, just a moment. So from that we can be able to calculate for the remaining value of Ix just by making Ix the subject. So from that we can get the value of Ix simply by making Ix the subject. From that we shall have that, therefore Ix is going to be equals to, this negative will go the other side and become a positive, so it will be 12.58 divided by 0.204. So when we do that, pressing that on the calculator, we shall have 12.58 divided by 0.204. And then after doing that, we have our current Ix being equals to 61.67 amps. So my Ix that I'm getting, the value of Ix that I'm getting is equals to 61.67 amps. So that is my value of current Ix. So from there, you can proceed. Now, when we find the current Ix, that means you can go back to this graph here, as we had drawn earlier on, and you feed in your respective values of Ix. So for example, my first value of Ix is 61.67. So this is going to be 61.67. Now here, after subtracting Ix minus 20, so I'll have my 61.67 minus 20, and I'll get that the value here is 41.67. Then when I do the same for this point here, I can get my Ix minus 60, which is 61.67 minus 60, and that is giving me a 1. The current flowing in this direction is 1.67. Okay. Now when I reach here, it's going to be my Ix, which is 61.67 minus the value here, which is 110. So this is giving me a negative 48.33. So the negative is simply implying that the current is not flowing in this direction, but rather than flowing in this direction. So the current flowing in this direction and the current is flowing in this direction. So when it becomes negative, we shall know that this point E is our point of minimum potential. Then similarly, let's calculate for the current flow in this side. It will be 61.67 minus 140. So that is giving me a negative 78. So this is negative 78.33. So the negative simply means we have a positive current of 78.63 flowing in this opposite direction. Okay. So here we have a 78.63 and here we have a 48.33. Just simply like that. So after finding your currents flowing in a particular section, you can find directly. Now here they didn't request us to find the voltage at each particular point, but they only wanted us to calculate for the minimum voltage. Now, looking at to that, from what I had earlier on communicated, that when we get a point whereby the current is changing direction, i.e. current is feeding from this side and feeding from this point, that point there qualifies to be called the point where the voltage of minimum potential occurs. Okay, so our point of minimum potential is point E, and therefore the voltage at E qualifies to be what we call the minimum voltage. So from that we can calculate for the minimum voltage. So let's calculate for the minimum voltage by looking at that point. So minimum voltage, minimum potential. The minimum potential is at point E. So the minimum potential is VE, okay, is what we want. So how do we find VE? To find VE is going to be equals to VB, okay. You can work from any direction which you want, but it is always good for you to look at this direction, which point is shorter, nearest to the nearest feeding point, and you work from that direction towards the center. So for example, if I'm to work from this point, I'll only need to calculate the voltage drop across this and also the voltage drop across this. But when I'm to work up from this direction up to here, I'll need to calculate the voltage drop across this also, and across this. So that means I have 3 more workings to do here. Here I only have to do 2 workings, okay? So how do we find voltage at E? Voltage at E, when you look at it from that angle, we can say voltage at E is going to be equals to voltage at F minus voltage drop between F and E, okay? But we don't know also voltage at F. So voltage at F will be got by getting voltage at B minus voltage drop between this section here. So it will be voltage at B minus the voltage drop between this point, which is V, B, and F. So thereby, that means we start by calculating for VF, then we can calculate for V at E. Hope we are together there. So at that point, we can get V at F. So using that same technique, we can say VF is going to be VB. Our VB was given to be 220 volts minus voltage drop between B and F, which is going to be equals to I between B and F times R, B, and F. So from that we shall substitute. This is going to be 220 minus the current flowing there is what we have calculated to be 78.33. 0.63. So it will be minus 70. It will be minus 78.63 times the resistance between B and F. So the resistance between B and F is what we got as our RFB, which is giving us a 0.034 from our previous workings. So we shall come here and we substitute for that value also, which is 0.034. And when you press that into the calculator, you'll have that your value is going to be 220 minus 78.63 times 0.034. So when you do that, it's giving me a 217. So this is giving me 217.326, which is can be written as 33. This is in volts. So but that is the voltage at F. So you need to get also voltage at E from what we had written down. So the voltage at point E is going to be equals to Vf minus voltage drop between F and E, which is IFE, times the resistance across that section, which is RFE. So this is going to give us Vf. Our Vf is going to be equal to the Vf we calculated here, which was 217.33 minus our IFE. Our IFE is going to be the current flowing in this section that we have calculated, which is 48.33. So we shall take that value of 48.33 and we simply feed it into a equation to give us 48.33 times the value of resistance RFE. Now our RFE, we calculated it also earlier on, which gave us this particular value, REF, which was also equal to 0.34. So therefore, we substitute for that value of 0.034 and we calculate. So this is going to give me 217.33 minus 48.33 times 0.034. Therefore, that is giving me an answer of 215.686, which can be rounded off to 7 volts as VE. Therefore, this is our minimum voltage and it is appearing across at point E. By doing that, we shall have finished calculating the entire question.
Because they don't ask maximum.
When they ask for maximum voltage drop, it can be this voltage drop between this point here, between this point and the point of minimum potential. So if you want to find maximum voltage drop, it is going to be equals to V at B, okay, the sum of the drops between this place here. So you get the voltage at this plus the voltage at this. Similarly, someone who will work out from this side also gets the same answer, just that for him we will need to calculate more. So it can simply be also voltage at point between the voltage drop between point A and point E, which is going to be equal to the sum of these drops, these 3 drops. So, but both of you will get identically the same answer as someone who has worked from this side and also someone who has worked from this side. So that is it. It's okay. Yes. Any other questions? If there are no questions, I think that will be our discussion for tonight. Mr. Henry, do you want to give a closing prayer? Or you have closed already?
No, the one opening the prayer can close. Me, I'll pray next time.
That one closed long time ago.
As is around.
Any other questions regarding to this session in particular?
I was just, if we had time, I was wishing we could do one more example,
Uh,
My,
but
my,
unfortunately, we don't have time.
my question is,
eh,
don't we, why haven't we multiplied the two? Because it is a two DCY system. Why haven't we multiplied the two anywhere? Or it does not apply?
we multiplied the 2 here. We multiplied the 2 when we were calculating for the value of resistances. So these 2, I said this 2 here is representing the 2 wire. This value of resistivity, and this is the length, and this is the area.
Okay, got you.
Yes.
Uh, for those who were supporters of Arsenal, Arsenal won 3-0.
Yeah, tomorrow is the party. Tomorrow is the wedding. Liverpool, Man U.
You were watching football in my session.
I said tomorrow.
No, Henry, he was
They have
watching.
sent me live score. They have just sent me a message.
Yes,
10,
yes.
10. Please prepare this shot.
The link.
10.
Yes.
10.
Yes, I'm getting you.
10.
Yes, I'm
Number,
getting you.
which is fed twice.
I'm also hearing you.
Let me
Both
te- let me just tell you to speak via.
share for me this number.
As if I've heard that what you say is share the link. You share the link. She has been up and down. She needs to.
No, she was saying that 10, you share your number.
But she knows my number. We shall share the link. Share the link after uploading.
But why is Sharon ever quiet? Sharon, can't you say something? Please say something. If not, give us the closing player.
Close your eyes and we pray.
Uh-huh.
Let's take away back. Oh,
Have you humbled yourselves? It's a word of prayer.
We are even meeting.
Sababu sabi.
Okay. Everlasting Father, we thank you for this day. We thank you for the gift of life. We thank you for this discussion that we have had. May you help us even understand more as we pass through on our own, everlasting Jesus. May you give us the gift of wisdom. May your Holy Spirit always be with us. Guide each and every one, everlasting Father. May you protect us throughout the night. And may you continue giving us the gift of life. In Jesus' name I've prayed. Amen.
Amen.
I have a suggestion for you 10-10 before we close.
What question?
My suggestion is
Everyone should switch on
we
their
should give
camera.
this opportunity of the prayers for the ladies. They can say good prayers than us men. And God listen to them more than us.
Okay. Otherwise, I think we should now call it a night. Have a good night.
Thank you so much.
We
Have a
shall
good night, guys.
we shall continue.